Alright, in this video I will discuss about my homework 7 of solid mechanics subject. In this homework, we will discuss about two questions. This is the first question. In this question, we need to determine the slope at support A, this part, and the deflection at point C, this part. The first that we can do is determine the free body diagram. This the support A have two reaction force at X and Y direction because it pin support, and the support B only have one direction to only the Y direction because it's roller support. After determining the FBD, what we can do is determining the reaction force. Then we got the sigma MA equal to 0, then RP and BY times L is that minus omega times A over A per 2 is in the middle of the uniform distributed load. Then RP we got the omega times A over 6. If we input the number that we got is 16.67 kilonewton. Then we go to the reaction force at Y direction is RA LM minus omega A plus RP equal to 0, and or we can write as this at A plus RB equal to omega A. We can write this like this way also. Then we input the number that already have RP is 16.67 and omega A is 100. This cut from the omega times the direction. Cancel this, and we got 100. Then Li is equal to 83.33 kilonewton. Now after we know the reaction force at each support, we need to determine the internal moment. We divide it into two parts. This is part A, C, and this is part C, B. This is the internal moment that we will get. Sigma m equal to 0 when minus Lix and omega x square. Or we can write m minus Lx equal to omega x times x over 2. Then we got the m equal to x minus 1 over 2 omega x square. Sorry, sweating is too bad. Then to find the deflection, we need to integrate this m twice, so we do the double integration. The first that we got is this one is the first integration, and this one is the second integration. We do similarly with the second part is the CB part, and we also got the m equal to RP. This is RP L minus x is where we want, when it's the point that we want. So if L equal to x, then x, then M equal to RB times L minus x. We do similarly again. We integrate twice to determine the deflection. This is what we got. Now after we know the equation of deflection, equation of the slope, we need to determine the boundary condition of the system. When x equal to 0 is happen here, there is no deflection here because the deflection might happen like this. When x equal to 0, the y is equal to 0, there is the deflection at point A. Then the second condition is x equal to L. X equal to L is here. Then y is equal to 0, there is no deflection also at this point, this P point. Then x equal to A, then x equal to A, then the dy over dx is, or we can also call it theta 1 equal to theta 2 is when the slope at this point. Then x, then the fourth condition is x equal to y equal to y, or we, for it easier is if we call it y1 and y2. Now we apply the boundary condition to the equation that we get before. The condition 1, we input to the this is the second integration of the first part. We input x equal to 0 and y equal to 0. Then we got the is 0 0 0 0, so the C2 equal to 0. For the condition 2, when x equal to L and y equal to 0, that we can input it to, also it's also the second derivation, second integration of part 2. It is part CB, and we got this input. This is 0, this is 0. When x equal to L, L equal to 0, this x, then we got this C4 minus C3 times L. Now we go to the third condition when x equal to A and theta 1 equal to theta 2. We input the first integration that we got in the first part and the second part, and we equal it. Then finally we got the C3 equal to C1 plus 7 over 12 omega A cube. Now we go to the second, the last condition, boundary condition, when x equal to A and y1 equal to y2. This is the second part of integration of the first part. First part it is for part AC. This is from part CP. We equalize it, and finally we got the C1 is 25 over 72 times omega A cube. Then this value is we get when we input all the constant from C1, C2, C3, and C4, and we cut this part. We got this. This is for the first equation is to finding the deflection. This is for the second equation. This is for finding the theta or the slope. Now we go to determining the slope at when x equal to 0. We just substitute the number that we get before. When 16.98, actually 98 times 10 to the power of 6 dy over dx, it's ei with inertia times the e equal to this to 0. This is 0, and we only have this. Then the slope that we got is 8.18 times 10 minus 3 rad. Then we go to determining the deflection at point C when x equal to a, then equal to 2 meters. We input the number and we cut this. YC is deflection at point C. When deflection at point C x equal to a, then we input this, we cut this. Then the final deflection is minus 0.78 times. This is equal to 11.70x downward. This is millimeter. And it's done for the first question. Now we go to the second question. For this question, we need to determine the slope at deflection at point C. It means that the deflection at point C is the max deflection. It's given that A equal to 200 GPa. For this question, it can be easier when we divide the load first. Divide the first load and the second load. We will use this equation, this important equation. We don't have to derive it because it's already we can find easily, and we can go easily. We will use these properties to find the deflection and slope at the end of C. Then the first that we can do after knowing that is find the FVD of the first load. This is first load when moment is applied. Reaction way. We don't have to use this reaction first. We only use this because we need to find the deflection. Then deflection, we don't need to determine the reaction force and the moment. We just need to input the number that we have. That's on the boundary condition. In this condition, when x equal to L, the deflection at the final. The deflection at this final when x equal to L, so we use this equation. We input the number to the equation when E is equal to for I for the beam, it is wide film actually, and the I is 2.62 times 6 to the power of 6 millimeter to the power of 4. Then so we got the deflection is equal to 0.00387 meter. It is downward, so make like this. Sorry. And like this. It is the deflection. Right. Then to find the slope at the end of is x equal to L. It's same with the deflection, x equal to L. The formula is given here. We can find it. Then we input the number. So this is based on the first load. The theta max is equal to this input. Input the number. Then we got minus 2.347 divided by AI. Then we go to the second load, it is at this point when A is equal to 0.75 and B is equal to 0.5. Oh yeah, then L is equal to 1.25 meter. We will use this boundary, these properties with the boundary condition given. At B, we need to find the slope based on load P. We will use this property. Wait, this properties because we need to determine the deflection at max at x equal to L. So like here, we will use these properties. Then after that we just easily input the number. Then we got this point. It's like don't work here. 0.01674 meters. Then for the slope itself, it's the same with the previous load, but the difference is the equation properties. We use this when x equal to or x equal to L. Then we got this point. Then after getting the deflection at the first load, the second load, the slope at the first load and the second load, we just need to calculate. So the total deflection is from the first load, it is the second load, then we get this number, the final deflection at max. This point. If we want to find the deflection at x equal to this, we just change the equation based on the properties, and the slope at C is this. We just sum the slope that we got from the first load, then we got from the second load, we got this. We just input the data EI, where E is 200 GPa and I is that point, then we got this point. So the total deflection is this, minus 6.32 times 10.3, or this one, if we convert it to degrees, is around 2 degrees rad times 180 over 5. This will, we want to convert the radian to degrees. Okay, thank you. It's all for me.